Hello again. One of my favorite kinds of graphs. Okay, it takes kind of a nerdy person to have a favorite kind of graph, but it's really useful, so trust me on this one. It's the velocity time graph. The velocity time graph is simply what it says it is. It's something that graphs velocity on the vertical axis. So up here would be velocity and time on the horizontal axis. So that would be right about here. Now, typically, if we're going to graph things, we need to have a unit. For time, I'm going to put seconds, but there's no reason that it has to be seconds. It could be minutes, hours, years. And over here, I'm going to put velocity, and we'll say that that's in meters per second. But again, it doesn't have to be meters per second, although it would be good if the denominator unit matched the unit on the horizontal axis. It doesn't have to, but typically it makes things a little bit easier. You see, the velocity time graph tells you a lot of wonderful things. One thing it tells you is the velocity. If you know the time, let's say some time here, you just go straight up to the graph, straight across, and right there you read what the velocity of the object is. It appears here that the velocity is increasing as time goes on. Now, don't make the mistake of thinking that this graph is somehow representative of the actual picture of the object moving. This is talking about, that is, this graph is describing an object that's moving in one-dimensional motion. It's moving in a straight line. It's just moving faster and faster and faster. Let's suppose that up is the positive direction. What this graph would indicate is that it's going faster and faster and faster and faster. Okay, that would be the velocity time graph here. But here's some interesting things. If we pick a time here, maybe we'll call that time 1, and another time over here, I'll call that time 2, and come straight up to the graph and come across to here, we could call this velocity v1. We could read it right off the graph. We could come up here and find this velocity, which we could call v2. Now, one of the things that you learned in Algebra 1 was how to compute the slope of a line. This happens to be a straight line, and you know that you compute slope by finding the rise here and the run here and taking rise over run. Mathematically, the way you learned it is that the slope is equal to, well, you probably in algebra class learned y2 minus y1 over x2 minus x1. Look at the graph. No x's, no y's, v's and t's. So in fact, it's v2 minus v1 over t2 minus t1. That's how you would compute a slope. Okay? Now, as it turns out, that means we have sort of a final velocity minus an initial velocity. What? Final minus initial? That's change. So this is change in velocity divided by change in time, right? Does that look familiar to anyone? No hands up? Come on, you know what it is. That's right. Change in velocity divided by the time over which that change took place is our very definition of acceleration. Okay, technically it's average acceleration, but we'll just go with acceleration for right now. And so what we have is the really important fact that the slope of a velocity time graph tells you the acceleration, because that slope is also called the rate of change. It's the rate of change of velocity. Got that? That's kind of neat because it works not just for straight line graphs, but for graphs that are curved too. Well, let's take a look at a somewhat simpler graph. Let's suppose we have a velocity time graph that looks like this. Once again, the velocity is here, and again we'll make it in meters per second, and time over here in seconds. But this time we're going to put some units on this thing. We're going to give it a little bit of heft. Let's suppose that the velocity is 8 what? 8 meters per second. By the way, you notice that as time goes on, the velocity stays 8 meters per second. That means it has zero acceleration. Whoa, look at it. Whoa, it has zero slope. Yeah, that's right. The slope and the acceleration are the same when you're talking about a velocity time graph. Let's pick a unit of time over here. Let's say this is 10 seconds. Okay, if I draw a line straight down from the graph to the 10-second mark right there? What is the area of this region in here? What is this area right here? Well, it's just a rectangle, so area is just base times height. And so the area is just, and I'm going to keep units in it here, 8 meters per second times 10 seconds. If you're paying close attention, you'll see that the seconds cancel here and here. And so we get an answer of 80 meters. That's an area? Well, it's an area of a graph, not an area of your carpet. So that makes sense when the graph has units of meters per second in the vertical direction and seconds in the horizontal direction. But something else that's really important about that number, isn't that how far the object would have traveled if it's going 8 meters per second for 10 seconds? Wouldn't it have traveled 80 meters? Yeah. So that, ladies and gentlemen, is the displacement. And so the area under the velocity time graph gives us the displacement. Let's try the same thing with this graph. We'll have the velocity again in meters per second over here, and the time over here in seconds. And let's suppose that right here, the object is traveling at 30 meters per second. Okay, starting at 0, so this object's speeding up. It's going faster and faster and faster. And right about at this time, the object's going 30 meters per second. Let's suppose that that happened after, let's say, 6 seconds. Okay. Well, now we know how to calculate the rate of acceleration. It's the slope. 30 divided by 6 is 5 meters per second squared. That's pretty easy. But how far did it travel in that amount of time? Well, how do we find the area of this triangle right here? Because that's what we're going to need to find if we believe that the area is going to give us the displacement. Well, let's find out. The area, which we believe is displacement, is, what's the formula for a triangle? Yep, 1/2 base times height. So that's 1/2 times the base, which is 6 seconds. I'll drop the unit now. Times the time, which is 30 meters per second. The seconds cancel out. We get an answer in meters. Half of 6 is 3, and 3 times 30 is 90 meters. Now let's see if that actually makes sense as an answer for the displacement. You see, we have here what's called uniform acceleration. And so that means the average acceleration is just what we have at the halfway point, meaning on average, not the average acceleration, the average velocity. On average, the velocity was 15 meters per second. And it averaged 15 meters per second for a time of 6 seconds. 15 times 6, 90 meters. I think we have a general principle. And so we can confirm that the area of a velocity time graph tells you displacement. Now this is why I call it the wonderful velocity time graph. You see, if you simply read the graph, it tells you the velocity. If you find the slope of the graph, it tells you the acceleration. If you find the area under the graph, it gives you the displacement. Now for nice straight lines, anybody with a basic understanding of geometry can do this. But if these graphs happen to be curved, you know how to find a slope if you know some calculus. It's called a derivative. You know how to find the area if you know some calculus. It's called the integral. All of this starts to connect together. Pretty neat, huh? Okay, let's try an example then. Let's suppose that this is our velocity time graph. And this time I'm going to have the velocity read in, let's go with feet per second, just to be a little different. I mean, we're in America here, so we can use feet instead of meters. And over here we'll have the time in seconds. And so let's divide up our graph into this point right here. Let's come down from here to this point. This point looks important. And of course, right here, this point is important. Let's have some time units. Let's suppose that this is 6 seconds right here. This is another 6 seconds, so this is 12 seconds up to here. This is 4 more seconds, so this is 16 seconds up to here. And this is 2 more seconds, so this is 18 seconds up to here. And let's analyze the heck out of this thing. Well, we need a little bit more information. We need to know, for example, what is this height right here? Let's make that a nice, simple 10 feet per second. Okay? Let's find the acceleration at the various locations along this graph. Well, right here, let's call this section 1. We'll call this section 2. This is section 3, and this is section 4. The acceleration in section 1 is just the slope. This point has a height of 10 and an x or a t position, that is time, of 6. So change in velocity is 10 minus 0 over change in time, 6 minus 0, is 10 over 6, or 5/3, or about 1.7 feet per second squared. Okay? About 1.7. It's 1.6 repeating. What's the acceleration in part 2? Well, a couple of ways of thinking about it. One way to think about it is the velocity is holding at 10 feet per second. It doesn't mean that the object stopped. It's still moving. In fact, it's moving the fastest it's going to move, 10 feet per second, but it's no longer changing velocity. Oh, wait, that means its acceleration is 0, right? Or you can think about it graphically. The slope is 0, so the acceleration is 0. Got it? Okay. Let's find the acceleration in part 3. And let's do it by the slope method. Final velocity minus initial velocity. And I'm going to use this right down here as our final. So the final velocity is 0 minus the initial velocity, which is 10, over the change in time, which is 16 minus 12. That's negative 10 over 4. And you can compute that pretty easily. That's negative 2.5 feet per second squared. Now, what does that mean? Well, negative acceleration, when it has a positive velocity, means that it's slowing down. And sure enough, as time goes on, the velocity goes from 10 to 8 to 6 to 2 to 0. It's slowing down. And then as it continues with that same negative acceleration, down here it starts to speed up. Whoa, that's kind of weird, isn't it? Well, remember, this is all straight line motion. That means along here, it starts at 0 and it speeds up faster and faster. Then it's moving faster. Then it starts to slow down right here. Right here, it comes to a stop, and then it starts to move backwards. So that's the graph, you might say, of the actual motion. Okay, but this is the velocity time graph of that motion. Okay, so right here would be at 16 seconds. Right here would be at 18 seconds, and so on. Got that? Okay, let's find the displacement. How far did it end up from where it started? Let's do it in sections. Okay, this area right here we'll call displacement 1. Triangle, so it's 1/2 times the base, 6, times the height, 10. Half of 60 is 30. Note the units. 6 seconds, 10 feet per second. Seconds cancel out. That's 30 feet. So it moved 30 feet in that amount of time. Over here is displacement 2. Finding the area of this rectangle, this length is 6. This height is 10. So it's 6 times 10. It moves 60 feet. Why did it move 60 feet in the same amount of time, 6 seconds, where over here it only moved 30 feet? Because over here it started at 0 and had to speed up to 10 feet per second. Here it was already moving 10 feet per second the whole time. Make sense? Okay. Displacement 3 is right here. And that is going to be, again, 1/2 times the base, which is 4, times the height, which is 10. half of 40, whoops, is 20 feet. Okay. But then right here, right there, the object has stopped, that's like here, and begun to move backwards. Let's see what this final displacement is. This displacement, we'll call it displacement 4, is 1/2 times the base. The base goes from 16 to 18, so that's 2, times the height. What is that height? Well, I'm going to have to extend my axis down a little bit here, and we'll find that this height is going to be about -5. You can check the algebra there. In 4 seconds it moved down from 10 to 0, so in 2 seconds it'll move from 0 to -5. Make sense? So times 2 times -5, and that is -5 feet. What the heck is that as an area? Well, again, remember, we're talking about an area of a graph. It can have any unit, it can have any value. Okay. Up here, when we talk about the real world and the actual motion of the object, it simply means it moved backward for 5 feet. So the total displacement of the object at the end of the 18 seconds is the sum of all the displacements. After all, that is what total means. So it's going to be 30 plus 60 plus 20 plus -5. That looks like 110 minus 5 is 105 feet. So we took a complicated motion and we discovered what its displacement is. Now, this goes to show you an important distinction between displacement and distance. The distance traveled by the object is it traveled 30, then 60, then 20, that's 110 feet. Then it traveled another 5 feet, so it actually traveled 115 feet. Its displacement is where is its final position relative to its initial position. Its displacement is a vector, and that displacement vector was 105 feet. Got that? The wonders of the velocity time graph and all the things that you can tell from it. Have fun with that. Practice a few more. Bye-bye.